Hello everyone, welcome back to another lecture of Chemical Process Design and Simulations, course code CHE446. So there are four zeros of this course. Zero number 1 is related to the fundamentals, zero number 2 is related to the simulation, 3 is related to analysis, and fourth is related to design. And our today's activity is linked with zero number 1, zero number 2, and zero number 3. If you remember in our previous video, I had told you that in lecture number 16 basically we had simulated CSTR and we had calculated the residence time of it. Then in lecture number 17 we had calculated the residence time for plug flow reactor, and in this activity we will be comparing these two reactors and we will be using the reactor system. Means we will be connecting CSTR in series, we will be connecting PFR in series, and then we will be calculating the resonance time and obviously for the same conversion. So we will be using the same exercise, and which exercise it is, for the conversion of cis 2 butene to trans 2 butene. And we will determine the conversion achieved if two CSTRs are used in series. Each CSTR has a residence time of 20 minutes. Now this is the target, that the residence time should be 20 minutes. If you remember or recall your previous lecture of CSTR, we had said that we want a conversion of 90%. And if you remember in the adjust tool, we had used the conversion, percentage conversion as 90%. But here the target variable is different. The target variable is the residence time of 20 minutes. And if you remember, we had calculated this residence time in the spreadsheet. It means we will be using the spreadsheet as target variable in this case. And I will show you obviously when we will go to the Aspen HYSYS. And there are two reactors. Obviously, the reaction set will remain the same for both. The outlet of the first reactor will be the inlet of the second reactor. So let's quickly go back to Aspen HYSYS and solve it. And for the same reaction system, this is your task definitely. That assume that the first reactor has a residence time of 30 minutes and the second reactor has the residence time of 10 minutes. But obviously, once you will be able to do this, you can easily switch to it. There is no issue. So as you can see, I have been using the same Aspen file which we had generated in our lecture number 16. And as you can see, for a recall session, that we had achieved the 90% conversion in this reactor, as you can see. And the spreadsheet, if you open it, the residence time was 39.13 minutes. And how we had achieved it? By using the adjust tool. But now there will be a difference, that we want to calculate the conversion. Now it is not our target. Our target is that the residence time should be of 20 minutes, and the conversion obviously that will be calculated for it. And obviously right now the residence time is 39.13 minutes, for which we are getting the conversion of 90%. So when it will reduce to 20, obviously the conversion will decrease, but that will be calculated by it. So what we need to do, the adjust variable will remain the same. In select variable, you need to go to the spreadsheet 1, and in spreadsheet this is B3, which is the residence time. If I take you back again to it, this B3 represents B and 1, 2, 3. This third represents the residence time. So what we need to do, go to select variable, go to this spreadsheet B3. Actually, it is not giving you any value because it is a calculated value not available in Aspen, or you can say library, because it's a tank volume, it's a nomenclature. Actual volume flow, it's a nomenclature, but residence time, it's a not the nomenclature. So select it and then select it as 20. And it is asking for more iterations to run obviously. So it is now converged. So first you need to check whether it is 20 or not. Definitely it is 20. So for 20, obviously we can say that the conversion would be less than 90%, because for a resonance time of 39.13 minutes, you was getting the conversion of 90%, and now it is lower, and you can see the conversion is 82.14%, and the reaction balance you can see it as well. So now what we need to do, we know that the vapor flow rate is 0, the liquid flow rate is same as that of the feed with the conversion. So what we need to do, go to this reactor, select reactor, which is the CSTR2, and connect liquid CSTR, which is the outlet of first column, to the inlet of second column, and we will label it as CSTR2. It will be vapor CSTR2. Its nomenclature, it's clearly up to you. Liquid CSTR2. And after specifying it, I had told you in the case of CSTR, the liquid volume should be 100%. Then specify the reaction set. And then there are two options. You can either start it, like give it again 0.05 cubic meter, and check the reactions. Obviously, this is a reaction conversion. I have used a dummy value. You can even proceed without it, or can give a dummy value to start it. Now, again, in the same way, first thing you need to do is to use the spreadsheet. If you remember the previous exercise, we had first used the adjust tool to get our required conversion. But in this case, our target variable is residence time, and it can only be calculated by this spreadsheet, which we have learned so far. So go to the spreadsheet again, the reactor volume, flow rate, residence time. So reactor volume, right click on it, add import variable, and it is a second reactor. Do remember it that you have selected the second reactor for it. If you select the first reactor, it will cause problem. Similarly, then select the flow rate of liquid CSTR2, and it is the actual volume. Flow, select it, done, and in the same way calculate B1 over B2 multiplied by 60. So it is 30.43, and your task is to take it to 20. So what you need to do, go to this adjust tool, place it over here. The adjusted variable definitely will be the tank volume of CSTR2, because we are now dealing with the second reactor. And in target variable, what it will be, spreadsheet 2, not the spreadsheet 1, because already we have done with the spreadsheet 1, and it is B3 selected, and the value should be 20. Unknown maximum minimum up to you, but started not conversion 10 iterations, increase 10, and it has been converged successfully. And if you want to know that in how many iterations it has converged, you can see here as well. So if you go to spreadsheet, the answer is 20, satisfied. And if you go back here, 82.1 for the same conversion as in the first reactor, and that makes sense that the resonance time in both cases was same. So definitely the percentage conversion in both cases will remain the same. So that's how you simulate the CSTR in series. And if I take you to the final value by going in worksheet in composition, you can see that the composition of cis to butane in the final one is 0.0319, and trans to butane is 0.9681. Means if I ask you that how, or the percentage conversion, overall percentage conversion of these two, so that is 96.81, which is shown over here. That overall it was 1 over 1 here, cis to butane value was 1, and at here in liquid CSTR 2, it is 0.0319. So it means if you FA naught minus FA over FA naught, if you calculate it, then 96 point multiplied by 100, definitely then it is 96.81% conversion in while connecting CSTR in series. So that is the first part of our today's activity. In the second part, we will be doing the same task for the PFR, and we have already done the same task for the PFR in our previous activity, which was lecture number 17. So if I scroll it down, and the PFR of our previous activity is placed over here. The feed conditions are same as that of CSTR. This is the PFR, and if I take you to the conversion of it, that going to reaction results, the percentage conversion is 90%. And we had in adjust tool, we have varied the tube length to get the 90% conversion. And in the spreadsheet, the resonance time was 10.37 minutes. And now what we are going to do, assume two PFRs are connected in the series. For the conversion of cis to butene to trans to butene, determine the residence time. Now you can see there is a shift that we had to now determine the residence time. So now it cannot be your target variable. You have been asked to determine the conversion. It would be, then residence time could have been your target variable, but definitely in this case, residence time cannot be your target variable, which is required to achieve the same conversion when two CSTRs were connected in the series. Obviously, I hope you have understood that we have connected two CSTRs in series. We know the conversion of both these reactors. That both for both these reactions, the conversion was 82.14%. Now we want to see that when the same conversion is coming in PFR, that for first PFR the conversion is 82.14, for the second PFR the conversion is 82.14. So what is the residence time which is required in PFR to achieve the same conversion which we have achieved in the CSTR? In CSTR, 20 minutes residence time was used or calculated or required basically to get the 82.14% conversion. But what is the residence time required in PFR? This is our basically the question. So I hope you have understand the question here as well. So what you need to do? There will be no change over here. Only this conversion should be changed. Otherwise, if you go back to the CSTR, here your target variable was residence time. You knew the residence time. You had to calculate the conversion. But here it is asking to calculate the residence time and you know the conversion, and the conversion is coming from this CSTR, which is 82.14%. Let me take you back again. Here it is 82.14%. Here it is 82.14%. So for both PFRs, we will be specifying the conversion as 82.14%. So go to this adjust tool and specify target variable as 82.14. Not solved, reset it, and it is okay. Obviously, you need to reset to rerun it. And by going here and in results, you can see the conversion is 82.14%. Now we need to go to the spreadsheet tool to see that for the CSTR, for the same conversion, the residence time was 20 minutes. But the residence time here, it is 7.636 minutes. As you can see, approximately 2.7, 2.8 times lesser than the CSTR. Now what we need to do, connect this outlet PFR, which is the outlet of the first reactor, to the inlet of the second reactor. So how you can do it? Outlet PFR1, outlet PFR2. This is the optional stream energy. It's up to you if you want to specify it. Reaction set is specified. Unknown dimension, 2-inch diameter we had selected here, and 1 meter length is selected over here. And then we need to specify the pressure drop, which we are not assuming in this case. So you can see 24.8% conversion. So obviously we need to vary the reactor length again to get the required conversion. And how we can do it? By using the adjust tool. So here the procedure is same. If it has asked you to calculate the conversion, then obviously in the target variable, the residence time would be the specified value. What do you need to do? Vary the reactor length, which is PFR 100. Obviously we haven't changed the name, and it is the tube length. And in select variable, which is the target variable, the percentage conversion in second reactor, which is 82.14%. The same conversion as that of the CSTR. Started, not solved. Again, go for 10 iterations. Whether it is solved or not, yes, it is solved. And in 16 iterations, basically, as you can see at just 4 iteration 16, it has been converged for the same conversion as that of the CSTR. So as you can see, 82.14 conversion is achieved. And if you go to worksheet and composition, you can see 0.9681 final conversion. The final values are same for both outlets from both PFR and CSTR. 0.9681 of liquid. Skip this. No vapor is involved. So its composition is useless. So as you can see, for both reactors, the conversions are same. The final outlet composition is same. Now we want to calculate the residence time for the second reactor. So we have select PFR 100, reactor volume. We will select it. We will done it. Then we will select the flow rate of the outlet PFR 2, the second PFR outlet, and actual volume flow selected, done, and then B1 over B2 multiplied by 60. 7.787, and here the value was 7.636, minor difference obviously. So that's how you basically simulate both PFR in series and CSTR in series. So that's it from this lecture. We have done the analysis part, we have compared both, and we can say with confidence that for the same conversion, the CSTR required more residence time and the PFR requires less residence time. So that's it from this lecture. Thank you so much.